The dream of interstellar travel has long captured the imagination of humanity. We can all see how far progress has come in space exploration. But what if one day there was a concept that could radically change our understanding of speed and the distance of space travel? It was so ambitious that it led scientists and engineers to search for ways to take us beyond our solar system. What was behind this project that could turn dreams into reality? And how did it influence the future of space technologies? If you're curious to learn more, don't forget to like and subscribe. The Orion project was a manned nuclear pulse spacecraft development program conducted in the United States during the 1950s and 1960s, aimed at exploring interplanetary and interstellar space. The concept was proposed by Stanislaw Ulam and Cornelius Everett in Los Alamos in 1955. According to their idea, the spacecraft would move using a series of hydrogen bomb explosions ejected behind it. These detonations would vaporize special metal disks, turning them into expanding plasma that would push the spacecraft forward. In 1957, the development continued under Ted Taylor, one of the leading American specialists in nuclear warheads. Working at General Atomics, he actively advanced the project. Later, Anglo-American physicist Freeman Dyson joined the effort to assist with further development. The work involved both theoretical calculations and experimental tests. One of the tests involved flight trials with small models using chemical explosives as a driving force. These devices were called put-puts, or hot rods. Although some tests resulted in destruction, in November 1959, one trial successfully flew 100 meters, confirming the possibility of stable pulse propulsion. NASA also developed a Mars mission profile based on the project, proposing a 125-day round-trip flight with 8 astronauts. To test the durability of the thrust plate, experiments were conducted on the Eniwetok Atoll. During the experiment, steel spheres coated with graphite were placed 9 meters from the nuclear explosion's epicenter. Despite the powerful shockwave, the spheres remained intact, though the graphite layer completely vaporized. The spacecraft was planned to be launched from the Jackass Flats atomic testing site in Nevada. To overcome Earth's atmosphere, the vehicle needed to have a streamlined, bullet-like shape. It was to be placed on 8 75-meter-high launch towers, designed to shield it from the shockwave of the first explosion. At launch, each second would be accompanied by a detonation of a 0.1 kiloton charge, and after reaching space, the interval between explosions would increase to 10 seconds, using 20 kiloton warheads. The cost of launching 1 kilogram of payload was estimated at $150. How long would it take to build such a giant spacecraft and launch it into space? What technologies could allow achieving speeds close to 80% of the speed of light? The high thrust and specific impulse characteristics of nuclear pulse drives suggest that they could be used not only for interplanetary, but also for interstellar travel. Freeman Dyson calculated that a spacecraft using megaton thermonuclear charges with high exhaust velocities, ranging from 3,000 to 30,000 kilometers per second, could reach a maximum speed from 750 to 15,000 kilometers per second, which is up to 5% of the speed of light. 2 designs for interstellar spacecraft were proposed: energy-limited and momentum-limited. The energy-limited Orion Starship design was enormous. Its reflective plate had a diameter of about 20 kilometers, allowing it to efficiently cool between explosions without using ablative materials. The plate was to be a copper hemisphere weighing more than 5 million tons, capable of distributing heat without disintegrating. The total mass of the ship would be 40 million tons, of which 30 million tons would be fuel, and the remaining 10 million tons would be used for structure and payload. By detonating charges every 100 seconds, the ship could accelerate to 0.33% of the speed of light in 100 years, with a journey to Alpha Centauri taking about 1,300 years. This design would be a generation ship, ensuring the survival of humans throughout the entire journey. The momentum-limited Orion Starship had more modest dimensions and used ablative cooling of the plate by spraying graphite lubricant between explosions. This reduced the payload, but allowed for a more compact and faster ship. The plate diameter was only 100 meters, and its mass was 400,000 tons, with 300,000 tons allocated to the megaton charges. Such a ship, detonating a charge every 3 seconds, could reach 10,000 kilometers per second in 10 days and travel to Alpha Centauri in 130 years. The energy-limited Orion Starship project cost around $3.67 trillion at 1968 prices, which was equivalent to the annual GDP of the United States. The momentum-limited Orion Starship was significantly cheaper, about 10 times less. Later studies showed that a spacecraft with a thermonuclear pulse drive could accelerate to 8% of the speed of light. In turn, a hypothetical photon pulse spacecraft, using the energy of matter-antimatter annihilation to power the drive, could theoretically reach 80% of the speed of light. However, despite promising developments, the project was ultimately cancelled. One of the main reasons was the signing of the Partial Test Ban Treaty in 1963, which introduced a ban on nuclear explosions in space. This decision was driven by serious concerns about potential radioactive contamination. Thus ended one of the boldest and most revolutionary ideas in the history of space exploration. Had the project been implemented, the exploration of deep space could have taken a completely different path. However, even though the project was closed, its developments influenced subsequent research in interplanetary travel. Subscribe to the channel and stay updated to learn more about forgotten yet incredibly fascinating pages of science and technology history.